This video will guide you through Chapter 23, Inferences About Means, the Hypothesis Test. We will learn the material by working through a problem. The problem that I've selected has to do with my dream, which is a coffee vending machine. I believe there should be one in every faculty room. So in this imagined world, we have a coffee vending machine that is supposed to pour a 10-ounce cup of coffee. But after trying a few cups of coffee, I suspect that I'm being shorted. So for 20 days, I gather evidence. You can see the data that I've gathered below. Why don't you pause the video for a minute while you enter the data into your calculator. You can enter the data by going to your calculator and pressing Stat, Edit, and then in L1, why don't you enter in the data? Okay, so I assume that you have all 20 days entered in. So in order to conduct a hypothesis test, just like when we were doing proportions, we are going to assume for the null hypothesis that the average of the amount of coffee that I have received over these 20 days is equal to the 10 ounces that they say they're going to. So we're going to say the null hypothesis is that mu is equal to 10. Oh, we were 10. All right, so remember, this is mu. This is not x bar or y bar. Mu is the parameter for mean because we want to know something about our population. And we're the skeptic, so we assume that the coffee machine's doing exactly what it's supposed to. The alternative then, because I think I'm being shorted coffee, is that on average, the mean is less than 10 ounces of coffee. And just like for every other hypothesis test that we've done, we have had some conditions that we've had to meet, and they're going to be slightly different for this test. So our first condition shouldn't look very much different, and it's that we have a random or representative sample of coffee. So while it's not necessarily a simple random sample, I have reason to believe that my coffee selection is representative of all of the coffee. Okay, so we are going to assume that we have a representative sample of cups of coffee. And secondly, we want to establish independence. So for 20 days, I gathered my data. And so I'm going to assume that these 20 cups of coffee is less than 10% of all cups of coffee that this machine will put out. So 20 is less than 10% of all cups of coffee from this machine. And we have one more condition. It's not going to be the success-failure condition because we're not dealing with a success-failure Bernoulli trials type of situation here. So we're going to have to actually return to this condition. So why don't you scroll to the bottom of your page, because this is where we have to talk about some things that are going to be a little bit different about this test. So why don't you go to the bottom of your page, and we're going to take a few notes. So I just want you to think about, we're talking about means here, and a little while back when we were doing the sampling models for means, we said that means are going to be distributed normally, and they're going to be centered at mu, which is the population mean, with a standard deviation of sigma over root n. And so that seems fine, except that sigma represents the population's standard deviation. And while I have an assumption about what mu is in this problem, remember I'm assuming that mu is 10 for this problem, I have no assumption or no information to go on about what sigma is for the population. So I have a problem. So in this case, just like we had to do in earlier cases for proportions, we're going to have to estimate this. And what I do have to go on is the standard deviation for the sample. So I'm going to estimate with S. All right, so we're going to, instead of doing sigma over root n, we're going to do S over root n, and that is now going to be called the standard error. But we run into one more problem by having to use the standard error. So you wonder, what other problems could we possibly have? All right, so when we have an estimate, remember we're trying to estimate the mean, but now we're also using an estimate for standard deviation for that. So remember back when we would talk about putting two distributions together where we were unsure about one thing and then we're unsure about the other, and so now we're even more unsure. This is kind of a case like that, where actually we have two things that we're not really sure about. So we're going to be more unsure. Our distribution is going to be wider. So in this case, we're going to have to account for that. So we can no longer use the normal model. Because particularly for small sample sizes, the normal model is going to be a little bit too narrow for us because we have increased variability. And remember, that's because we don't know our standard deviation. All right, so we have increased variability, we don't know our standard deviation, and for small samples, that's not good. So there's another model that's been developed, and it's called the t-model. All right, so we're going to learn the t-model this time. And the t-model looks actually very much like the normal model. If this is what the normal model looks like, then the t-model is also going to be unimodal and symmetric, but it's just going to be a little bit wider. So if this is normal, this is t. All right, and actually, as our sample sizes get larger and larger and larger, our t-model starts to look more like the normal model. So as n increases, t begins to look more normal. All right, so that means that the t-model is changing based on the sample sizes. So the t-model has a parameter that's associated with it called degrees of freedom. So what you're often going to see is this, T subscript df. And that df stands for degrees of freedom. And degrees of freedom are simply the number in your sample size minus 1. Okay, and we can talk more about that at a later date, and there's a huge section in your book about it. But for right now, it doesn't really matter. Okay, we're just saying that as n increases, your degrees of freedom increase, and your model changes and becomes more normal. That's really all you need to know about that for right now. And I'll show you how to use the t-model in your calculators in just a second. Okay, so we're going to scroll back up, and now we're going to be able to address these conditions. So we said there was one more condition left, and the t distribution does not work for really skewed distributions. So what we're going to have to check is that our data, or our sample, is approximately normal. That is unimodal and symmetric. Okay, so if we have the data, that's great. We can just go to our stat plot over on our calculators. We're going to turn that plot on, and we would like a histogram, and we put our data in L1. So we can say zoom 9, and there it is. And you need to have evidence that you've actually checked it. So you're going to go back to your paper and you're going to sketch what that looks like. All right, so it's approximately unimodal. It's not wildly skewed. Actually, a lot of things will meet the condition of being unimodal and symmetric. If you don't have the data, then they're going to have to tell you in the problem that the population is approximately normally distributed. So you would have to either be able to look at the data or have that information in order to move on. So these are your three conditions for continuing with the problem. Okay, so with this problem, in the mechanics section, we need to certainly have our sample mean. All right, and now we realize that we also have to have our sample standard deviation, because we're going to use that in our calculation for standard error. So remember, you can get your sample mean by going stat calc 1var stats, and we can see right here our x bar, or y bar we're going to call it over here, is 9.845. And our S, we do not want sigma right now, we want S. Okay, so we want 0.199. And N is equal to 20. All right, so now we're ready to go forward with our test. So we're going to draw, oh, and so this S allows us to get the standard error of our model. So we have a T model. It's a lot like the normal, but we're going to write over here that we have a T model with 19 degrees of freedom. So that's how we're going to write it. All right, so T, 19, centered. We assumed that we were centered at 10. And we have to calculate our standard error in this case, and our standard error is going to be S over, well, why don't we just replace it and call it 0.199 divided by the square root of 20. And so we'll go back to our calculator and we'll say 0.199 divided by the square root of 20. And that's 0.044. And we're comparing our mean, which was 9.845, and we want to see if we are that far below. All right, so just like every other problem, we want to calculate the z-score. And the z-score is going to be 9.845 minus 10 over 0.044. So 9.845 minus 10, and I'm just going to leave my answer in there and go second answer, and we get negative 3.48. Okay, so we know we're pretty far below the mean, which if we were using the normal model, we would feel pretty good with saying that the coffee machine is shorting us coffee. But remember, this T model is a little bit wider, so it may not be quite as meaningful, and this area may actually not be quite as small as it would have been if it was the normal model. So in order to calculate the probability that we have a z-score that's less than negative 3.48 when we're using a T model, looks just like we used to do for the normal model. We go to second distribution, and instead of normal CDF, you can see that you have TCDF. So we're going to scroll down to TCDF. And our inputs are pretty much the same. We're going to go from negative 99 to negative 3.48. But we also have to tell it how many degrees of freedom we're dealing with. So we're going to put in 19 degrees of freedom. Enter. All right, so still a pretty small probability, 0.001. And that is your p-value. Okay, just like we were doing with tests for proportions. All right, so our mechanics are done. We have our p-value calculated. All our work has been shown. And so we're ready to move on to the conclusion. This conclusion should not look very much different than the conclusions we've been drawing before. Okay, so due to a low p-value of 0.001, we will reject the null hypothesis. There is strong evidence to claim that the coffee machine is shorting Miss Darling, and I assume everybody else, coffee. And that's all that we have to do for a one. Oh, that's the one thing I forgot. We call this a one. Where did I forget to do that? Up here. We're doing a one sample test for means. That's the name of this test, and we are going to want to name this after we check our conditions. All right, so that's it for a hypothesis test. The next video will be on confidence intervals, and we'll reuse the same problem. Before we move on to do the confidence intervals, I just want to make sure that you know another way that we can also do this problem on our calculators. So if we go to Stat, Tests, there is a t-test here. And that's essentially what we're doing. We're doing a one sample t-test for means. So we're going to click down to number 2. And our input in this case is data. Okay, sometimes problems won't give you data, they will give you the statistics. So I'll show you actually what that looks like first. So if you were given the statistics, you would be given the sample mean and the sample standard deviation, and you would put those in there. But this time we actually can just read our data right in. So it'll save us a little bit of time. So our null hypothesis was that the mean was equal to 10. We're reading our data in from list 1, so it's going to do all the calculations that we need. And we are testing the alternative that the mean is less than 10. So we want this guy over here. What happened? All right, scroll down. So we want this guy over here. And we're going to say calculate, and hopefully everything matches up. Okay, so we can see that the t-value is negative 3.49, which is very close to what we had there. List the x-bar, list the standard deviation, which is 0.199. Okay, but notice you still need to calculate the standard error here. All right. So we also have our p-value, which is 0.001, and that is actually also what we got. So you can do the test this way as well. All right, that's it. You can move on to confidence intervals.